Hello everyone to lecture 2 of BIS103 for the spring quarter 2020 here. What I want to do today is sort of move forward in our metabolism and bioenergetics topic. As you can see here on the screen, the focus will be to continue some of our overview of metabolism. We will dive into understanding more pathway directionality and energy. We'll be looking at some of the common enzyme reactions that will be important for the quarter. And we will start looking at our sugars or carbohydrates, as you can tell from the background for today's lecture. Please note that I have broken up the video into 2 parts. So this first part will be mostly looking at recapping some of what we had discussed in the previous lecture, as well as then talking about pathway directionality and how we can calculate it. And then the second part of the lecture will be looking at some of the common chemical reactions and really starting to focus in on our first big topic, the carbohydrates. And so for today's learning goals, again, you can find these also as individual PDFs on Canvas, so you can prepare yourself. Again, these are sort of the major topics we want to cover and that will be relevant for the exams. So there are a few here today. What we want to achieve today is to be able to describe concepts of pathway cooperation and directionality. This will have to do a lot with Gibbs free energy, the way pathways operate here in the second part. And then we want to start to be able to explain some of the structural and biochemical properties of our carbohydrates, sugars, as one of the major energy resources in terms of metabolism that we have. And we'll follow up with actually applying some of these different approaches to recognize and draw carbohydrate structures. So this is really meant to set us up to understand the biochemistry and the structural differences in carbohydrates as a foundation to then really understanding how they are formed and how they're being broken down. Right, just as a recap, right, last lecture video, we had spoken about these opposing pathways, catabolic pathways here that break down more complex metabolites such as carbohydrates, fats, proteins into smaller compounds, and we'll see for the most part we're actually breaking them down into carbon dioxide, water, and ammonium. And then on the opposing side, we have the anabolic pathways where we use precursor molecules, less complex molecules, amino acids, sugars, fatty acids, some nitrogenous bases, we will see those. And we can build up from these precursors more complex macromolecules. Again, here our proteins, our sugars, lipids, and so forth, that you see over here again as a more complex one that we mostly get through our food. And then we had discussed that these 2 opposing pathway concepts are linked directly through just a handful of common metabolites, specifically here ATP, NADH, NADPH, and FADH2. These are now compounds that will carry the energy that we have released in these catabolic pathways, breaking down complex molecules. And this energy that is now stored in these metabolites that we got through the catabolism of complex metabolites, we now can use for these build-up reactions in the anabolic pathways to generate more complex metabolites. And so an important concept here was that it's really helpful for metabolism to have this common currency of just a handful of metabolites that can do this transfer of energy in order to be able to interconnect all the many pathways that actually make up metabolism. Right? We had said that this extremely dynamic network, and in order to coordinate and allow cooperation between these pathways, a common currency is extremely helpful. And just to recapture this here, right, some of these pathways that we see really are highly interdependent. They cooperate, not all of them, but in many cases, different subsets of metabolism, meaning different metabolic pathways. They are not independent of each other, they cooperate. And so the main purpose of this is to obtain chemical energy. chemical energy that we can then translate into biochemical work, into sustaining life. There are essentially two major subforms that we want to look at here. First one being, right, for autotrophic organisms, we can capture solar energy, meaning photosynthesis. That's one way of doing this, and we'll get to this at the very, very last lecture. Mostly for the next lectures, we'll focus on using oxidation reactions. So oxidizing energy-rich chemicals from the environment, meaning from our food, and in oxidizing those, releasing the energy, and then storing them in this common currency. The other reason to cooperate for pathways is that it allows pathways to convert nutrient molecules. So metabolic intermediates, right, we had said some metabolites may be products from one enzyme or substrates for the next, meaning they are intermediates in the pathway, that they can convert these metabolites from more complex ones into simpler ones, into monomers, and eventually into waste products that we then excrete that don't hold any further energy that is useful to us. On the third point here, we can also go the other way around. Right now in the anabolic pathways, we can take these monomers here and we can convert them into polymers. So large numbers of these now connected smaller metabolites, and we can use this to generate, for example, proteins, larger scale carbohydrates, nucleic acids, so DNA and RNA, as well as lipids, and we'll look at all of these metabolite classes throughout the quarter. And so really what we're doing here, right, is to synthesize and degrade, meaning to interconvert these biomolecules. And this is actually happening all the time. This is not static events, one after the other. The synthesis and degradation of different metabolites into each other is really constantly occurring in any living system. And so in a way, we can demonstrate this in this triangle here, that we have a constant flow of energy between the generation of energy through breaking down more complex molecules. And then if we don't need the energy right away, we can use pathways that allow us to store this in energy-rich metabolites, or we can utilize it directly to use this energy to build something else, right? So we have this constant interconnection of energy flow through biochemistry between these three different purposes. And so again, we mentioned, right, metabolism is extremely dynamic, extremely complex. You see all these different pathways here on this slide. And if I just zoom into a small subset of this, you can see how these pathways cooperate. If you, for example, just take this section up here, right, you have a pathway that is sort of going along this way. And again, right, these dots are metabolites, apologies. The lines are now enzyme reactions from one metabolite to the other. And you can see one going this way. And there are a number of pathways that interconnect through different metabolites here. And so these all cooperate using the same intermediates. So this is very important, and it also should highlight to you, it's not only important to understand where these pathways intersect, right? Where are these points of common use of metabolites, but also in which direction are they going, right? So that's the next step, is understanding direction is really critical, right? If I don't know if this pathway fluxes, for example, in this direction or in the other direction, I will not know with which pathway, whether, for example, with this one here or with this one up here, this one pathway may interact at any given time or in any given condition. So understanding the directionality in the context of the organism, an organ, a tissue, a cell, and so forth, is really critical to understand metabolism and how these pathways can cooperate and how they do so. And so going back to our original slide here, showing these anabolic and catabolic pathways, what we want to do then with this directionality is to understand metabolic flux. So meaning how much of a given metabolite is converted in a specific direction, all right? And so what we're looking at essentially is the net flux, right? We need to realize that, right, these anabolic pathways here and the catabolic pathways here, it's not that they don't occur in a combination with each other. They do happen at the same time. It's not that, right, the anabolic pathway functions, then stops, and the catabolic starts. They do occur at the same time. And what we want to understand as metabolic flux is essentially the net flux, right? So the rate of the forward reaction, say the anabolic reaction, minus the rate of the reverse reaction, so the catabolic reaction, okay? So this is what we want to be looking at. Understanding this flux will give us an understanding of what is the likelihood of a pathway running in the forward versus the reverse reaction. And so this is what we call pathway directionality. And the formula that we can use to calculate this is Gibbs free energy. And this is probably something you have already heard about in some of your previous classes beforehand. And so we won't go too much into how this formula was developed. We really want to learn how to apply it to understand metabolic pathways. And so to do this, right, we can use Gibbs free energy, or delta G, to predict the direction. And what this means is simply the thermodynamic possibility of a reaction to occur in a specific direction. Okay. And so G here in Gibbs free energy, what it actually is the amount of energy to do work. And it's important to note here that this is considered at constant temperature, or T, and constant pressure, or P, and is expressed in joule per mole. Okay. So how can we apply this? How does this work? Let's assume we have sort of a simple pathway, right? We have two metabolites here. These are our substrates, A and B. We have an enzyme here, right? And we have two products here, C and D. So this enzyme will catalyze this conversion, right? And so if you note here, right, I drew this arrow here in both directions. That means the reaction can flow in both directions. And so just to highlight this a little bit, it's really important in biochemistry to pay attention to our arrows, right? So if you, for example, draw an arrow only in one direction here, such as this means the reaction will only flow in this direction, right? From left to right. You can draw the arrow in the other direction. Now it's actually running in the opposing direction. And in some cases, you will see arrows that look like this. These are now reactions that can flow into both directions. So they're bidirectional, either direction is possible. In some cases in your book, you might find examples such as this, where you have a shorter arrow and a longer one. This gives you an indication of which one is the preferred direction of a reaction to occur in, right? So the direction and whether they go in one or two directions is really important to understand. And so these arrows essentially are based on the knowledge of pathway directionality that people have gained from understanding the Gibbs free energy for simple reactions such as this one indicated here, as well as more complex ones. Right? And so how can we use Gibbs free energy now to predict pathway directionality? Right? So what we want to look for is essentially the energy difference here. Right? So the delta G, and that is defined by the energy that is in your products here, minus the energy that is in your reactants, in your substrates here. And now you can imagine there are different scenarios. Right? So the first scenario would be if your delta G is smaller than 0, right? So in this case, the reaction would be spontaneous from left to right, and that we call exergonic. Okay. So what happens in this case is that your reactants are high in energy, and the conversion to their products will actually release energy. So the energy of your products here is smaller than that of your reactant, so the conversion can release energy, meaning now the reaction can run spontaneously, meaning it's thermodynamic possible from left to right. Okay. In the opposite case, so what happens if our delta G is greater than 0? Right? In this case, the reaction is not spontaneous, and we call this anergonic. Right? So in this case, it's the opposite is true. Right? Now, your products have a higher energy, and so what you have to do to enable this conversion is that you actually need additional energy added to your reactants in order to do the conversion to the products. So this reaction cannot be spontaneous, therefore, it is called anergonic. Right? But please keep in mind, this is very important, only because it's not spontaneous thermodynamically doesn't mean this reaction doesn't occur. What it means is that it now would flux into the other direction, right to left in this case, if we are comparing it to our example A up here. Okay. The third possibility now would be if our delta G is actually 0, and in this case, the reaction is at equilibrium. Okay. In this case, the energy of your reactants and your products is exactly the same, so there is no net flux in either direction. But again, keep in mind, this doesn't mean none of the reactions are happening. It just means that both directions are happening at the same rate of flux. Okay. That's what we would call equilibrium. So this is just for definition. How do we calculate this now? Right? We had already mentioned several times now that pathways are made up of complex networks. How can we calculate a delta G in a complex pathway network? And just to start and understand this and provide opportunity to predict the directionality of individual enzyme reactions or pathways, one way to do this is to standardize the conditions. Right? And for Gibbs free energy, there are a number of conditions that we can standardize, right, to better understand and to simplify the system, essentially, to start and understand these predictions. Right? And some of the values that we can standardize I have listed up here in the corner. So we have our temperature, which is standardized at 290 Kelvin or 25 degrees Celsius. We have R here for our gas constant. Our pressure is standardized at 1 atmosphere. And then this is really important. The concentration of reactants over products is standardized as 1 molar. And I'll get back to that in just a bit, why this is important. And then there are a few additional aspects for biochemistry that are important to standardize here. One is the concentration of water, which usually is considered to stay constant in biochemical reactions. And we standardize it at 55 molar. And another one that's important is our pH, that for biochemical systems, we will standardize at pH 7. So this is different from what you may have seen in physics lectures, where standard pH is usually at 0. For biochemical systems, we're using the physiological pH, which is at around 7.0. And so taking this into account, so simplifying the variation within the conditions of a pathway, we can use these standard values to calculate our standardized Gibbs free energy, and this we call delta G0 prime. In some of your textbooks, you might find delta G prime 0. There's some variations in textbooks, but it means exactly the same. It is your free energy under standardized conditions. Okay. And so the way we calculate this is that we include it with our gas constant, the temperature, and then the natural log of KEQ. Right? So what's KEQ? Right? KEQ, as you can see here, is the product over reactant concentration at equilibrium, so at no net flux occurring. And so this is where our standardization of 1 molar comes in and where it's very important. So what we're looking at for the KQ, for every pair of a reactant and a product, basically what you would do is you set it at 1 molar each, you let the reaction run to equilibrium, and whatever concentration of product over reactant you end up with is the standard constant of equilibrium, so the KEQ at this point under standard conditions. Okay. And so this really helps us because doing so and standardizing the concentration gives us a mathematical relationship between the equilibrium of each pair of a reactant and a product to our standardized Gibbs free energy. Okay. And this can be measured, right? So we can measure these KEQs, and measuring those really helps us to now, under these standardized conditions, to be able to calculate the free energy of a reactant to product pair and to predict what direction a enzyme catalyzed reaction would flux into under standard conditions. Okay. So this can be very helpful. But, right, keep in mind, we're biochemists. Usually reactions don't occur under standard conditions. So we really want to know how does it work if we do not apply these standardized conditions. So what's happening under non-standard conditions? First thing we should be thinking about is what is not standardized in a living system, right? What is changing? And sort of the important parts are listed up here. Right? Some that we can maintain as constant is like the temperature. At least there are certain ranges we can look at, and our gas constant remains constant. And for the most part, our pressure is also considered to be constant. But concentrations of products and reactions really change in biological systems all the time, especially if you keep in mind that pathways cooperate and interact with each other. And so to calculate now our free energy under non-standardized conditions, we have another formula here. It's highlighted here. So our free energy under non-standardized conditions is now our value for the free energy under standardized conditions, plus our gas constant, our temperature, and the natural log not of KEQ, but Q. Right, so what's Q? Again, if we go back to this very simple pathway here, we have our two substrates, enzyme catalyzed into two products. Q now is the individual concentrations at this time of our two products, C and D, and the concentrations of our substrates. And that's what we call the mass action ratio. Okay. So the difference to KQ here is simply that we haven't started at 1 molar. Right? So still we're looking at the ratio of products over reactants, but we haven't started at 1 molar. We are starting at the concentrations that we have in the system right now under the conditions we want to look at. So for a biochemical system, it is really important to note that while the standardized Gibbs free energy, delta G0 prime, is really helpful to predict directionality, the really important criterion for measuring the directionality of pathways in a living system is our non-standardized conditions, is delta G. Okay. And by the way, for these formulas, you do not have to memorize them for any of the quizzes or exams. I'll provide them for you. There's no need. Those can be read up in any book. What I really want you to learn here is how to apply them to pathway systems. All right, so what we've looked at so far, right, is one enzyme reactions. How about if we now looking at pathways, right? We said it's a series of events, so multiple reactions catalyzed usually by different enzymes work together within a pathway. So in the simplest form, right, now we have this pathway here, right, going from our substrate A to our intermediate B, and then there's another enzyme that will convert this into our product C. What does this now mean for our KEQs and our standardized free energies? Okay. So good news is it's actually fairly simple because pathways can cooperate and because we have this mathematical relationship between delta G and KQ, these are actually additive. So the delta G0 primes of these individual steps, so the step from A to B and B to C, are additive to calculate the delta G0 prime of the overall reaction. And I highlighted this here. So you simply can add them up and you come to the delta G0 prime for the entire pathway. And obviously, right, you could add now here furthermore reactions and do the same thing, they're additive. What I want to draw your attention to though is because we have a logarithmic relationship to KEQ here, our KEQ values are multiplicative, not additive. They're multiplicative, okay? So the same would be true. You would have your KEQ for your reaction A and B, your KEQ for your reaction B to C. If you want to calculate the overall KEQ for the entire reaction A to C, they're multiplicative. Okay. All right. That's all great theory and calculating. I encourage you to work some of the practice exams and some of the quizzes that are in the study aid. So there are a number of questions that relate to calculating this. And so we can obviously work some of these in the office hours, but I would encourage you to work through them yourself and see how you do in applying these formulas to this purpose. Okay. How does it mean now in reality? I want to sort of highlight just basically our first major pathway. We want to look at our sugars, all right? And so the first reaction that I want you to look at is this one here, from glucose, which we abbreviate GLC. And please pay attention to the abbreviations we're using. GLC is glucose. If you do GLU, that would be glutamine. That's an amino acid. That would be wrong. So if you want to be safe, write it out as glucose. Okay. And so the reaction we're looking at here, this is actually should be a plus. I apologize for that. So it's glucose, and we're adding 6 oxygens to that. And through the entire pathway, what we are generating and converting the glucose into is 6 carbon dioxides and 6 waters. If I'm doing the delta G0 prime calculations from up here for this entire pathway that involves a whole number of enzymes, and we'll go through these throughout the quarter, I'm coming to a value of minus 2,870 kilojoule per mole. Right? And so now you can ask yourself the question, if it's spontaneous, right? It's a very negative delta G0 prime. And if you just go a little bit back in the video and look at our 3 categories, A to C, right? We had said that a reaction that has a delta G0 prime of less than 0, it would flux spontaneously left to right. So this value here would indicate to you, right? Yes, this reaction should absolutely occur spontaneously, should absolutely be thermodynamically possible. And so now to challenge you is, right, what about reality, right? What if you just put a bowl of sugar on the table, right? Thermodynamics would indicate now that while being on the table, that sugar should be spontaneously converted into our carbon dioxide and water, but nothing's happening, right? So how can that be? Why is this not following this rule? Right? And so here is where enzymes come in. Right? If you look at this graph here, right, we have our Gibbs free energy on the Y scale. We have our reaction progress on the X-axis. We have our reactants here and our products here. Right? This difference here, right, is your delta G. So this value here, right, almost minus 3,000, smaller than 0 should be spontaneous, but in reality, we actually have to overcome this hurdle here. That's called activation energy. You probably have heard of this in some of your previous classes too. So in order for this to actually run spontaneously, we have to overcome this activation energy. In reality, this actually has to do with the stability of the pathway intermediates. And the key players here are the enzymes. So the enzymes allow us to actually take the reactant and be able to overcome the activation energy here so that the reaction can flux according to its thermodynamic possibility. Okay? And what the enzymes do for the most part is that they can stabilize intermediate states of metabolites that have a lower energy. We look At some examples throughout the quarter, we won't go into too much detail, but basically through the stabilization, enzymes can lower the energy of these metabolites, thereby can lower this activation energy, can overcome this hurdle, and can allow this reaction to flux left to right now. What we call this is that enzymes lower the kinetic barrier, basically by controlling thermodynamic potential, right? So our delta G here is a thermodynamic potential. It's very large to flux left to right. And the enzyme here, by controlling our step over this energy hurdle, are controlling this potential, meaning for the reaction to occur. And so this is just for your information, just to have sort of the values as one summarized table. Again, here are the formulas. You don't have to memorize them. They're here for you. What you can see here also is summarizing what we had shown before, right? The relationship of KEQ and delta G. If you have a large KEQ, delta G will be negative, which means the reaction will flux spontaneously. If KEQ is 1, your delta G will be 0. This makes sense because we have a logarithmic relationship between KEQ and delta G. And the opposite is true if you have a small KEQ, you have a positive delta G, meaning now the reaction is fluxing in reverse. Okay. All right, I'll end here. This is part of the next video, so chime into the next part of this video and we'll start talking about some chemical bonds and our sugars.